previous distributions that we dealt with were all discrete distributions. So we looked at tables that were discrete probability distributions, as well as the binomial distribution. In those cases, there were exact whole numbers that the distribution could take on. That's why they were called discrete distributions, because the information that they were processing was discrete. Where we're moving now is towards continuous probability distributions. Continuous probability distributions can take on an infinite number of values between a certain number of values. So basically, what we're dealing with here is something where instead of only having 0, 1, 2, or 3 as the possibilities, you can have 0.37 or 1.278. So it's going to open up a lot more possibilities and make us look at things a little differently. Where we're going to start is with the uniform distribution. So when we're dealing with continuous probability functions, for all of them, the probability needs to be expressed as an area instead of individual points. Since there's infinitely many points within the area, really seeing it as geometric area and using that to tell probability is the best way to find these probabilities. Graphically, we're going to shade the area we're talking about to display which portion of the graph we're finding the probability of. And the main continuous functions we're focused on for this class are the uniform distribution and the normal distribution. The normal distribution is by far the most important distribution in statistics. We're going to do a number of lectures on it. We're going to use the normal distribution then to do confidence intervals, to do hypothesis testing. Basically, the entire rest of the class is built around the normal distribution. But before we get to that, the uniform distribution is going to give us a better idea of what continuous distributions look like without getting into all the nuts and bolts of the normal distribution yet. So we don't really need to know this word for word. This slide might be a little confusing, at least it has been in the past. But basically what it's saying is in the uniform distribution, everything is equally likely. So in the entire area, it's all the same chance of happening. For instance, maybe I just arrived at the subway and I don't know how long it's going to be until the next subway car gets there. I could see that as a uniform distribution. Let's say cars come every 6 minutes, where I could be waiting 0 minutes, I could be waiting 6 minutes, or I could be waiting anywhere in between. In that case, what f of x would be is 1 over 6 minus 0, or any 1 minute stretch in there has a 1/6 chance of the subway car coming. The way that I find the probability of any specific stretch within that window is I take b minus a, or the start of when I care about finding the probability, subtracted from the end of where I care about. So let's say if I'm going to come down and try and wait for the subway, what's the probability that the car comes between minutes 2 and 3? To do that, I would take the end of that window, 3, minus the start of that window, 2, and divide it by the end of the whole area that it could be, 6 minutes, minus the start of the whole area could be 0 minutes. So you're going to see a lot of these in practice, but basically what you should get out of this slide is that we're taking the shaded portion that we care about the probability of over the whole area when we find the probability between two numbers within a uniform distribution. Graphically, what's happening here is this whole area total equals 1, or 100% of everything that can happen. The portion that or the probability of any 1 unit distance here is 1 over b minus a. So if, for instance, b was 5 and a was 0, this would be 5 units long. Any 1 unit within that would have 1/5 probability of occurring. So if this went from 0 to 5, the probability of being between 3 and 4 is 1/5. Situations where you'd use the uniform is when you're concerned with events that are equally likely to occur, and when it's spread over a set interval with a starting and ending point. So let's say that we wanted to look at the uniform distribution that spread from 0 to 20. Any 1 unit interval in there would have a probability of 1/20 of occurring. This is a graphical distribution where I like to call it drawing the box. So it looks like a rectangle, The start of the box or the start of the rectangle is 0. The end of the box or the end of the rectangle is 20. Throughout this, the probability stays 1/20th for any one unit that I go in between here. The probability of getting any individual sample point is 0, because really there's infinitely many values this could take on. If I took 1 over infinity, mathematically that has to give me 0. Probabilities are always expressed as the probability of getting less than something, the probability of getting more than something, or the probability of getting in between two values. So, let's say I wanted to find the probability of getting less than 2. Graphically, here's what's happening. I take where 2 occurs in my box, I shade everything to the left back to the start of the box. The way that I calculate this probability is the numerator is the shaded area. So the numerator, the end of it is 2, the start of it is 0. So on top of my fraction, I'm going to write 2 minus 0. The bottom or the denominator of the fraction is always the whole box. So the end of the box, 20, minus the start of the box, 0. On top, we have 2 minus 0. On bottom, we have 20 minus 0. 2 minus 0 is 2. 20 minus 0 is 20. So we have 2 over 20, which reduces to 1/10. That's the probability that I will fall in this shaded region. So again, we take the shaded area. 2 is where it ends. 0 is where it begins. So on top, we have parentheses. End of shaded minus start of shaded, 2 minus 0. On bottom, we have the whole area of the box. So we have in parentheses, end of the whole box, 20, minus start of the whole box, 0. When we simplify it, 2 minus 0 gives me 2, 20 minus 0 gives me 20, and then 2 divided by 20 reduces to 1 over 10 or 0.1. If I wanted to find the probability we were between 4 and 15, the math stays the same. On top, end of the shaded area 15, minus start of the shaded area 4. On bottom, end of the box 20, minus start of the box 0. So this becomes 15 minus 4 over 20 minus 0, which is just 11 over 20. If I put in my calculator to get it as a decimal, it would tell me 0.55. Let's say we had a word problem. Word problem tells me the time it takes for a newborn baby to smile for the first time is uniformly distributed between 0 and 23 seconds. We want to graphically find the probability that a baby smiles between 2 and 18 seconds. Then we want to say if time to smile was uniformly distributed between 8 and 23 seconds, what's the probability that a baby's first smile falls between 12 and 23 seconds? So you'll see that this changes things up a little because our starting point's no longer 0. Let's see how it looks graphically. So here when we have 0 to 23 and we're looking for between 2 and 18, we look as the top of the fraction being the shaded area, end point to starting point, the bottom of the fraction being the whole box, end point to starting point. So shaded area is 18 minus 2, which gives me 16. Whole box is 23 minus 0, which gives me 23. I then have 16 divided by 23, which I can get as a decimal answer of 0.70. When the box is now restricted to starting at 8 instead of starting at 0, instead of everything being 1 over 23, it's now all 1 over 15. That 1 over 15 comes from 1 over the end of the box 23 minus the start of the box 8. But the question we've been asked is what's the probabilities between 12 and 23 seconds? So here's where 12 falls, here's where 23 falls, we shade that area. I can then say the top of my fraction is the end of the shaded area, 23, minus the start of the shaded area, 12. And the bottom of my fraction is the whole box, 23, minus the start of the whole box, 8. 23 minus 8 is 15. So I would get 23 minus 12, 11 on top, 23 minus 8, 15 on bottom, to tell me the probability that I'd fall between 12 and 23 is 0.73 or 73% of the time. Let's say ACE Heating and Air Conditioning Service finds that the amount of time a repairman needs to fix a furnace is uniformly distributed between 1.5 and 4 hours. Let X equal the time needed to fix the furnace. We want to first find the probability a randomly selected furnace requires more than 2 hours, and then the probability of randomly selected furnace requires less than 3 hours. To do it, what I recommend is starting by drawing your box. So my box should start at 1.5 and go up to 4. Then for each of A and B, I'm going to shade a different area. In A, if I want it to be more than 2 hours, I'm going to draw a line at 2 and shade to the right till I get to the end of my box. If I want to find the probability it's less than 3 hours, I'm going to draw on a line at 3 and shade to the left to find it to the end of the box to find the probability of less than. So here's what more than looks like. I put in the 2, I shade to the right of it. Now that I've got it drawn, I can use the same technique as before. On top, the numerator is 4 minus 2 for the end of the shaded area to the start of the shaded area. On bottom, the denominator is 4 minus 1.5 for end of the box minus start of the box. That's why I end up with 2 divided by 2.5, which ends up being 0.8 or 80% of the values. If I do it for the less than 3 hours, I draw the line at 3, I shade to the left up to the end of the box. So my shaded area is 3 minus 1.5. The whole box is 4 minus 1.5. When I do that out, on top I get 1.5, on bottom I get 2.5, and that division gives me 0.6 or a 60% chance.